This visualization shows the Standard Model's Lagrangian equations, assuming reality is dictated by perfect mathematical symmetry. But observing the actual universe, that perfection breaks down. Physics is defined by severe imbalances, charge parity violations, matter dominating antimatter, and an irreversible arrow of time. For decades, theoretical physics has framed these observational realities as flaws, deviations from a balanced mathematical ideal. In 2024, researcher Philip Randolph-Lillian proposed a framework that discards this assumption entirely. The hyperdimensional hypersymmetry theory, also known as HHHCR, argues that asymmetry is the active creative engine of the universe. Without an inherent imbalance driving differentiation, the cosmos would remain a dimensionless, timeless, and sterile potential. The theory begins with a concept called hypersymmetry, denoted as H, a hypothesized state of absolute, dimensionless unity where all potential interactions exist without differentiation. To see how our physical reality emerges from that unity, we can map the entire theoretical architecture. The descent from hypersymmetry into the observable universe is governed by one specific mathematical relationship, A equals H minus R of H. Here, A represents the observable asymmetry group set, H is hypersymmetry, and R is the reduction operator. Unpacking this reduction operator tracks how absolute potential translates into structured reality. The reduction process originates within hypergravity, the foundational geometric framework that embeds hypersymmetry. Operating within this framework is the first component of the reduction operator, coherence fields. These fields act as active, stabilizing translators. They stabilize the transition from higher dimensional potential, so the resulting reality does not disintegrate into chaos. The second component acts directly upon these fields. These are the asymmetric resonance operators. These operators break perfect hypersymmetry by injecting an asymmetry-inducing term, denoted mathematically as gamma sub n of x, into the coherence field. This specific term forces the undifferentiated potential to adopt a localized hierarchy and strict directionality. Physical dimensions emerge precisely from this interaction. The resonance operator fractures the symmetry, and the coherence field stabilizes the resulting structure. Unlike string theory, which relies on compacting extra dimensions out of sight, this model treats dimensions as a continuous unfolding process. This is called hyperfractal layering. A specific scaling function operates on a higher dimensional manifold, causing it to scale and split into distinct layers. To avoid collapse, each emergent layer stabilizes by resonating at a characteristic frequency within the larger hyperfractal structure. This mechanics directly applies to what we consider the fundamental forces of nature, the electromagnetic force, the strong force, and the weak force. Under the HHCR framework, these forces are not fundamental mathematical symmetries. They are frozen asymmetries. When hypergravity is reduced into a specific four-dimensional layer, it leaves behind residual artifacts that we observe as gauge fields. The established rules of particle physics, therefore, must operate strictly as local shadows of a higher-dimensional hypergravity asymmetry. This creates a conflict with classical mechanics. Noether's theorem dictates that continuous mathematical symmetries correspond to a conserved physical quantity, like energy or momentum. If resonance operators explicitly break continuous symmetry to generate reality, those conservation laws should theoretically fail. To resolve this, Lillian extends the classical math into what he calls the asymmetric Noether's theorem. This equation shows the hypersymmetric Lagrangian transitioning to a conserved current. When a lower dimensional symmetry breaks, conservation is not lost. The equation shifts the conserved property to higher dimensions, accounting for it with a new variable. This new variable, the fractal correction, provides a mathematical basis for higher dimensional properties to compensate for lower dimensional symmetry breaks. The coherence field dynamically adjusts this fractal correction in real time to maintain the integrity of the total system. Across these dimensional layers, asymmetry itself becomes the conserved property that stabilizes the universe. This logic extends to the nature of time. Within the unbroken master state of hypersymmetry, time does not exist. Time is an emergent property. To achieve an irreversible forward flow, a mechanism must force that timeless potential into a specific directional state. This occurs when a temporal asymmetric resonance operator acts upon the coherence field. This operator relies on a specific asymmetry-inducing term, gamma sub t of t. Rather than creating a neutral dimension, this term forces a unidirectional gradient that aligns perfectly with the second law of thermodynamics. The coherence field does not reverse entropy. It actively locks it into an irreversible forward progression, preventing systemic collapse. The relentless arrow of time is simply the continuous, stabilized operation of hyperdimensional asymmetry generating entropy. This theoretical architecture is dense, but it offers empirical utility by making specific, testable predictions. In high-energy particle physics, those predictions center on the fractal correction term. This 3D vector map of a particle collision illustrates the prediction. During extreme collisions, precise measurements should reveal anomalous missing energy. This missing vector corresponds directly to the fractal correction, shifting energy into higher dimensions. Moving from the quantum to the cosmological scale, the theory provides a model for stellar plasmas and large-scale magnetic fields. It predicts that the U1 asymmetry of electromagnetism, when interacting with hypergravity, will leave unique structural signatures across the cosmos. The cosmic microwave background provides a second scale to test for hyperdimensional coherence. Researchers are directed to look for subtle polarization patterns and small-scale temperature fluctuations in the CMB data that align directly with hypergravity predictions. Detecting these precise anomalies at both the subatomic and cosmic scales would provide the empirical validation required to confirm hyperfractal dimensions. The HHHCR framework suggests that perfection and symmetry are sterile. Every gauge symmetry, every particle mass, and the forward march of time itself rely entirely on the fracturing of that mathematical perfection. If the mathematics of this theory hold true, the imbalances of our universe are precisely the mechanisms keeping reality from collapsing back into the void.